Hey, today we will see the so-called Tate diagonal, which is a very mysterious feature of spectra. So we will end up constructing it, and then we will also see what this has to do with the so-called Siegel conjecture and power. I'm Achim Krause from Mathematics Münster. Before we can talk about the Tate diagonal in spectra, let's consider some kind of analogy or toy example, which is, let's think about abelian groups. So in abelian groups, if you try to write down a kind of diagonal with values in the tensor product of A with itself, right? You can write down a set, like a map of sets, which sends X to X tensor X, no problem there, but this is not a homomorphism, right? And you can easily see that, because if you see where X plus Y goes to, then it goes to X plus Y tensor X plus Y. If you multiply that out, you do get terms X tensor X and Y tensor Y, but you also get some kind of arrow term, which is of this form, X tensor Y plus Y tensor X. And one thing you can ask is, what kind of quotient do I get if I try to pass to the minimal quotient of this, where this map is actually a homomorphism, right? So in other words, what do I get if I quotient this guy by these error terms? And here's a better perspective on these error terms, right? Remember that from our discussion of the Tate construction, we saw these norm maps. So in the Tate construction video, we discussed these on the level of spectra, where there were certain maps out of the homotopy orbits into the homotopy fixed points. But of course, you can also take an algebraic analog of this, which is a norm map which goes from the actual orbits to the actual fixed points, right? And so what did this map do? Well, elements in here are of course represented by just elements of this p-fold tensor power. And so you can ask, where does x1 tensor xp goes to? And well, this goes to the sum over all group elements of the corresponding cyclic permutation of my elementary tensor. Right? This defines a map from A tensor P to A tensor P between these tensor powers. And evidently, this thing is in the fixed points. It's invariant under cyclic permutation. But also, the map evaluated on a specific element does not change if I precompose with the group action, right? So in other words, this also factors through orbits, right? So this assignment defines a map like this. And one way to think about these error terms in the diagonal, here we've taken p equals 2, we've taken the twofold tensor power. But in general, so one thing you see here is this element is of this form, right? It is obtained as a norm for p equals 2 under just application to x tensor y, right? And so here's an observation. If we put all of this together, which is the diagonal from A to the p-fold tensor power, which simply sends an element to X tensor and so on. So this is just a map of sets. This induces a homomorphism from A to the p-fold tensor power, and it even lands in fixed points, clearly, modulo the image of this norm map. In other words, if we divide out by elements in the image of the norm, we really do get a homomorphism, right? So we're just saying that sort of the error terms that obstruct additivity of this map are in the image of the norm. And secondly, and that's maybe the part that's a little more tricky, secondly, this homomorphism exhibits this quotient, this co-kernel of the norm, as A mod P. What do I mean by that? Well, I simply mean that this map is actually surjective, and its kernel is precisely P times A. So, in other words, this induces an isomorphism from A mod P to this guy. Okay. So I want to pose this as an exercise. And the first part is more or less what we just said about error terms. So this is something you should definitely check for yourself, but this is kind of more straightforward. For the second part, you need some trick, right? It's not even obvious that the map is surjective, let alone that the kernel is PA. And so as a hint, I would recommend to first check a special case of this statement, right? So in particular, what this is saying, this isomorphism, is that this functor here, which takes an abelian group A to this kind of quotient, is surprisingly additive, right? This doesn't look additive because you have these tensor powers here, but for surprising reasons, this quotient actually becomes additive. And try to check that first. And once you know that, I claim you can first check this for finitely generated abelian groups and then for all abelian groups by checking it in special cases using this additivity and so on. Right. So this is kind of the blueprint of what this Tate diagonal in spectra is supposed to be. And so let me give you the corresponding theorem right away. And the theorem is the following. There is a unique Lax symmetric monoidal natural transformation from the identity to the Tate construction of the CP action on the p-fold tensor power. Right? If you take a p-fold tensor power, there's going to be a CP action permuting the factors. I mean, even a sigma p action, but we're restricting to CP. And we're taking the Tate construction of this spectrum with CP action. And so I guess I said natural transformation. I wrote some pointwise thing, but of course I'm viewing this as a functor from spectra to spectra, and this as well. And both are Lex symmetric monoidal functors, and I can ask for a natural transformation compatible with the Lex symmetric monoidal structure. Right? This guy here is Lex symmetric monoidal because you can check that both the functor which takes a spectrum to its p-fold tensor power and the Tate functor are Lex symmetric monoidal. Okay. So let me say that explicitly here. So this is a natural transformation of functors sp to sp. Right. And so this is what we will discuss today. Try to understand where this map comes from and what some of its surprising properties are. And note that we can't proceed as we did for abelian groups, right? On the level of abelian groups, this was actually induced by a map of underlying sets. So that's going to be harder here because you don't really have an underlying set. You could try to discuss underlying spaces, but the underlying space of the Tate construction, the loop's infinity, is going to be a little bit complicated. It's not just going to be the p-fold tensor power or something like that. Okay, so the way we will proceed is we will first check certain properties of the functor which is the target of this Tate diagonal. And this functor, which takes a spectrum to its p tensor power and then takes the Tate construction, this is also known as the topological Singer construction. So let me call that Singer construction here. The Singer construction, which maps a spectrum X to this X tensor P Tate CP, is actually, surprisingly, an exact functor. So it takes cofiber sequences to cofiber sequences. And note that that's not true before you take Tate, right? This X tensor to the P is not even additive. So we have to kind of exploit some properties of Tate here. And just to get a feeling for what's going on, let's first check a special case. So, and that special case is to check that this functor is additive. So let's look at the case where we have a spectrum Y which splits as X plus Z. So in this case, as I already said, the tensor power is not additive, but we can explicitly see by how much it fails to be additive. X plus Z, and then the p tensor power. This splits by sort of, I guess this is some kind of categorified binomial theorem or something like this. This does have two summons, X tensor P and Z tensor P, but then there's some kind of cross effect happening, which is a sum of certain mixed terms. For example, there are P summons which all have P minus 1 factors X and 1 factor Z. There are P choose 2 many summons which have P minus 2 factors X and 2 factors z. And of course, these are not just abstractly this number of summons, but one way to think about these is that they're really indexed by subsets of a p-element set, right? You give me the set of indices 1 to p and a subset of that, and I give you such a term where I've taken for each index which is in the subset a z factor, and for all the others an x factor, right? So this, for example, corresponds to all the 1-element subsets, this to all the 2-element subsets, and so on. And from that description, you can also see how the CP acts, right? So on this guy and on this guy, it just permutes the factors. But on this summand, for example, right? Remember, this corresponds to these like 1-element subsets of all the indices from 1 to p. If I act by cyclically permuting them, all I'm really doing is I'm permuting these summands. And similarly, the same thing happens here. I'm permuting these summands because what's happening here is that the action of the cyclic group of order p on the set of 2-element subsets on the set 1 to p is again free. So, and I guess this is kind of a categorified version of the statement that these binomial coefficients are all divisible by p. Or I guess one way to prove that, actually. So what does this tell us? Well, this tells us that all these error terms here that make this functor, tensor power p, non-additive, all of these are induced modules over CP, right? All of them are just free in some sense. I'm just permuting some summands. And so these induced terms vanish after blank Tate CP. Because if you remember, the Tate construction, that was one of its key properties. It kills spectra where the CP action is induced. So all of these here, let me maybe put them in parentheses, all of these go away after Tate. And then you see that after Tate, we really have an additive functor. So what about the general statement? Well, it turns out you can do the same kind of trick. So for the general statement, we think of a cofiber sequence, x to y to z, as a two-stage filtration on the middle term, on y, where we think of x as kind of the filtration bigger or equal 1 stuff, and then we have zeros. So why is the z not here? Well, the z is here, but it's here as the 0th associated graded, right? So if I draw in the associated graded terms of this filtered spectrum, I guess non-negatively filtered spectrum, right? I could also extend by y's to the right, but let me just go to the index 0 here. If I draw in the associated graded, then, well, y mod x is z. That's where our cofiber sequence comes in. X mod 0 is x, and 0 mod 0 and so on is just 0, right? So we have a filtered spectrum with underlying spectrum y and associated graded given by x plus z. And we also get a filtration on the tensor power, where we start with the tensor power down here, and then in degree p, we get the tensor power on x. because here x kind of had degree 1. So here we're putting it in degree p. And over here we're putting kind of mixed terms. Here we're putting a term where we just have one factor of y and p minus one factors of x, and so on, all the way down to the kind of second to last term, which has one factor x and p minus one factors y, and then one summand here. And again, here we have like p summands, and here we have p summands, and in the middle the number of summands will be more like binomial coefficients. So, of course, this is not something I just guessed. There is, in fact, a monoidal structure on filtered objects, which is called the Day convolution structure. And this behaves in such a way that if you take the p-fold tensor power of this filtered object, you get a diagram like this. But morally, you should just think of the fact that somehow this behaves in such a way that over here x was in filtration 1, and so over here everything will be in the filtration according to how many factors of x it had. Right, and one of the key properties of this Day convolution product is that the associated graded is multiplicative with respect to that. So here, the associated graded will be the tensor power of z, p summands of one copy of x, and p minus 1 factors of z, and so on, all the way to p factors of x. And so we see that somehow after passing to the associated graded, we get something that looks like this again. And so what this means that after Tate, so this is the associated graded, and after Tate, we have just x tensor p, Tate CP, and all these other guys become 0. And then we have z tensor p, Tate CP. And as this guy was a filtered object with underlying thing y tensor to the p, after Tate, this, like what I'm getting after applying Tate to this diagram will be a filtration on y tensor p Tate CP. But it will have this associated graded, right? And so we get an exact sequence or a cofiber sequence with bottom thing, or like which starts with y tensor p Tate CP, goes to x tensor p Tate CP, goes to y tensor p Tate CP, and then z tensor p Tate CP. So exactly what we need for this to be exact. Right? And maybe a more down-to-earth way of thinking about this is this diagram, since all the cofibers of these first few maps, all except the last one, since all the cofibers of these maps are trivial under Tate, they're all induced. This means that these maps here all induce equivalences on Tate. So Tate of this guy over here gets identified with Tate of this guy. So in some sense, the cofiber sequence we have down here is just the cofiber sequence we get here from the observation that the associated graded term is this z to the tensor power of p. Right. Okay, so for weird reasons, if we're honest, this functor is exact, even though it's kind of made from at least one non-exact functor. And why am I saying that this is weird? Well, let me remark that at this point it's really dangerous to simply think of suspension as a shift, right? Because you might think that, oh, if I have some spectrum x, then sigma x is kind of the same spectrum, just in 1 degree higher. And then if I take the p tensor power of that, that's just going to be the same spectrum as the tensor power on x, just p degrees higher. And that's all not technically wrong, but note that the exactness which we just proved tells you in particular that the Singer construction, this functor, commutes with suspension. Right, so in particular, this shows that if I apply this construction to sigma x, I get sigma x tensor p Tate CP. So in some sense, this sigma here pulls out, but not as sigma p, as it would from the inner guy, but as a single sigma. And that's really weird if you think about it for a little bit. If you think about it more, then of course this just tells you that you have to be a little bit careful with the action here. And the reason is you can write this guy, the tensor power, as SP tensor, the just tensor power of the unsuspended guy. That's definitely true, but the CP action that you get on the left here is not just the shifted CP action here. This involves the, let's say it involves a non-trivial action on SP. And one way to think about that action is, so this SP is the suspension spectrum of the P sphere. And you can actually think of the P sphere as obtained from a p-dimensional R vector space of your choice by one-point compactifying. And it turns out the CP action on this guy is compatible with that description, but the vector space you have to take is not the R to the P with the trivial action, it's R to the P with the regular representation, right, where you permute the coordinates cyclically. So let me just write here, it's the regular representation sphere. And so that, just as a little warning, this is maybe a bit confusing, but it comes from the fact that if you take this regular representation sphere, that the Tate construction is actually the same as the Tate construction on the S1 with the trivial action. Right, so this is potentially weird, but it's definitely necessary for being an exact functor, and it all checks out. Right, so what does this help us, knowing that this is an exact functor? So remember, we wanted to construct a natural transformation from the identity functor on spectra to our exact functor. So sounds a little bit like a task for something like the Yoneda lemma. And in fact, there is a stable version of the Yoneda lemma, which let me just call this stable Yoneda here. So let me give this to you completely generally. So for an arbitrary stable infinity category, we have that, well, you can consider the category of exact functors from C to spectra. And the category is itself stable, right? Because you're just taking cofibers and fibers in the target. So functors into a stable category are stable, and exact functors are closed under cofibers and fibers, right? So we can take mapping spectra in that functor category, and this functor category also admits kind of co-represented functors. Because if X is an object in C, then you can consider mapping spectra out of X. And that gives you functors. So covariant functors. And they're also exact, because mapping spectra are exact in both variables because of stability. Right, in the general category, mapping spaces preserve pullbacks in the codomain and pushouts in the domain, but in the stable world, that just means that they're exact in both variables, if you look at mapping spectra instead. Right, so we can map out of one of these co-representable functors to any functor f, but we can also apply f to x and get a spectrum, right? F is a functor from C to spectra. And the claim is that there's an equivalence like this. And of course, this is some kind of natural equivalence and so on, where I want to remind again that we weren't very precise with how maps, like how mapping spectra and mapping spaces are functorial. So of course, to make this fully precise, one needs to input some of that as well. But sort of semi-informally, this is like a natural equivalence. Right, so how would you prove that? Well, it turns out you can reduce this to ordinary Yoneda. Where ordinary means ordinary infinity categorical Yoneda. So let me sketch this. So what is a natural transformation from this map x, comma blank to f? Well, both of these take values in spectra, right? And if you remember, a spectrum is just a sequence of spaces with identification between like loops of the next. So a map of spectra consists of just maps of all of these spaces together with suitable homotopies and so on. So this is the same as a sequence of natural transformations, let's say compatible natural transformations from, well, the underlying spectra, the underlying spaces. And the nth underlying space of f of blank can be written as loops of sigma n f, loops infinity of sigma n f blank. And the nth underlying space of the mapping spectrum similarly can be written as loops infinity of sigma n of that guy. And since map is exact in both variables, we can even pull that into the first argument. And since it's contravariant in that, it turns into a sigma minus n. Right. If you want to make precise what compatible means here, then you would just write the space of all such maps in a suitable way as a limit of spaces of maps like this. But I'll not do that. So what do we see here? Well, loops infinity of map. That's of course the same as just the mapping space, right? The one property of these mapping spectra we talked about at some point is that mapping spectra have as underlying spaces the mapping space. And so the ordinary Yoneda, right? This is now a natural transformation from a mapping from this kind of co-represented functor on C to spaces to some functor from C to spaces. So ordinary Yoneda tells you that this is a sequence of points in loops infinity sigma nf of sigma minus nx. But f is exact, so this sigma minus n pulls out, cancels with the sigma n here, and all of these are simply loops infinity f of x. And so we had like this word compatible here, and you can guess that while for an abstract functor where all of these spaces here are different, we get some maps between them and we're taking a limit. And so a choice of compatible such data is a point in the limit. But in this case, where all of them are the same, it turns out the maps are really equivalences. So the point, like a choice of compatible such guys, is just the same as a choice of point in this space. So what we get here is that the mapping space in this functor category from the co-represented functor to f, it agrees with just the space loops infinity f sigma x. And of course, I've given sort of an argument sketch on the level of points in various spaces. Of course, this is something one can make precise if you really state things in terms of mapping spaces and so on. Let me keep it at this sort of sketchy level. So this is something about mapping spaces, i.e. this statement up here, but just on the underlying spaces. And on the zeroth spaces in our spectra. But I'm claiming if you know this for all x, then you already know this. And a slightly informal way of thinking about this is that you can describe the nth space of these spectra by taking loops infinity sigma n of this, but then the sigma n pulls in. So the nth spaces, the equivalence between on nth spaces for x reduces to the equivalence on the underlying spaces here for sigma nx. And so if you know this for all x, this actually gives you this equivalence. there's a useful way of doing this in a cleaner fashion, where instead you talk about functors. You compare functors from a category from a stable infinity category to spectra, and left exact functors from your stable infinity category to spaces. And it turns out that's the same data. So this is like a left exact functor, i.e. preserves limits, to spaces, and this is the corresponding functor to spectra. And by knowing that that's the same, that these are equivalent, this kind of equivalence determines this. But let me keep it like this. Right, so at least informally, we've checked now that natural transformations from the identity functor to this Singer construction, x to the tensor p Tate CP, since this is an exact functor, correspond precisely to maps from S to S tensor P Tate CP. And of course, S is the monoidal unit. So the tensor power here is still the monoidal unit, and the action is trivial. So this is also the same as just S and then the Tate construction with respect to the trivial action. So there is an obvious choice of map like this, namely, we can take the composite where we go from S to homotopy fixed points with respect to the trivial action, right? There's always a map like this because this is just the mapping spectrum from BCP to S, sigma infinity plus BCP to S. And this guy is, I guess, the mapping spectrum from sigma infinity plus of the point to S. And so you can just pre-compose with the map from BCP to the point. Right? So we're using here that this was the trivial action. You don't have a map from the underlying spectrum to fixed points for a non-trivial action, but for the trivial action you do. Informally, this is some kind of statement like, well, if you acted trivially, then every point gives you a fixed point. But of course, this map is not an equivalence, so maybe it's dangerous to think about this too informally. Right, so we have this map, and then we also have the canonical map from homotopy fixed points to Tate CP. And that gives us a perfectly fine map, and by this Yoneda style observation, this gives us this Tate diagonal. Now I talked about this being unique, and of course there are more maps from S to S Tate CP. You could, for example, also take the zero map, and then you would get the zero map over here. So, but remember, part of the theorem I gave in the beginning of the lecture is that the transformation has to be compatible with the lax symmetric monoidal structures on both functors. So that includes being compatible with the unit. And you see that already being compatible with the unit determines what we do on S. Because this map here has to be the unit coming from the lax symmetric monoidal structure on the functor Tate CP. And well, it is that map because the monoidal structure on Tate CP is characterized by the Kan map being compatible with that. And this map here, that's a description for the monoidal unit in homotopy fixed points. Right, so we can only make this choice if we want this to be compatible with the monoidal structure. And in fact, this choice gives you something that's like symmetric monoidal. And a nice way to package what's going on there is the following lemma. I'll not prove that, but you can think of this as a kind of monoidal refinement of the Yoneda lemma. Or it's maybe a special case of a monoidal refinement or something like that, which is that this co-represented functor is initial in among lax symmetric monoidal functors. Sorry, lax symmetric monoidal exact functors from SP to SP. Right, and I'll not prove this, but I will remark that this boils down to understanding the day convolution monoidal structure on this functor category. Because it turns out, one way to think about what lax symmetric monoidal functors are is that they are algebras with respect to this day convolution monoidal structure. And secondly, this thing co-represented by the sphere, by the monoidal unit, is actually the monoidal unit with respect to the day convolution structure. And so if you believe that, then this lemma is obvious, because then this is just saying in any symmetric monoidal category, the unit is initial among commutative algebras. And that's not hard to see from the definitions. Right. So we'll not talk more about the day convolution structure, but if you know what it is, then this is how you can prove this. Right, so this gives us this Tate diagonal, and in the remaining time I want to talk a little bit about what that does for us. And so I guess here I'll stop proving things and just state things, because what comes now is among the most deep theorems in stable homotopy theory. Okay, so you might remember that for the cyclic group on P elements, the Tate construction, if we apply it to a spectrum such as HCP, tends to be some periodic thing, right? If we apply it to an Eilenberg-MacLane spectrum, it ends up being Tate cohomology of CP, which turns out to be some, for cyclic groups, some periodic version of group cohomology. And in general, for non-cyclic groups, it's still true that somehow if you take the Tate construction, the negative degree homotopy groups, if you take the Tate construction on an Eilenberg-MacLane spectrum, the negative degree homotopy groups will be group cohomology. But if we take X itself bounded below a spectrum, then in stark contrast to what I just said about taking Tate CP on Eilenberg-MacLane spectra, right? This tensor power is never going to be an Eilenberg-MacLane spectrum because we're tensoring over the sphere. So this is something complicated. Even if X was an Eilenberg-MacLane spectrum, this is going to be something complicated with a mysterious CP action. And in fact, this map exhibits X tensor P Tate CP as the p completion of X. And in particular, X tensor P Tate CP is again bounded below. So it's very much not periodic. And I also want to remark again that it doesn't, the connectivity of this guy is the same as the connectivity of X. So it's not even, like look at this, if you take X to be, say, K connective, then the p tensor power of X will be pk connective. But then suddenly if you take Tate CP, this will be just K connective. So for positive K, the Tate reduced the connectivity again, but it didn't make it periodic or anything. It's still it's still bounded below. It's just K connective. It's pretty crazy if you think about it. And so in particular, if you take the sphere, then this tensor power here is the sphere with the trivial action, as we've noted earlier. So if you take Tate CP on that, you're seeing that the Tate construction on the sphere is just the p completion of the sphere. This is very mysterious, right? This tells you that this is somehow something like Tate cohomology of CP with values in the sphere instead of an Eilenberg-MacLane thing. And this has completely different behavior from what you used to think of Tate cohomology. Right. So this in this form here, this is due to Lin and Gunavardena. You can think of this statement as a slight generalization of this. But for example, note that for X given by a finite CW complex, like a finite spectrum, it follows from this by the exactness of the Singer construction. So this statement is more or less, like this is more or less the heart of that statement. And there is some generalization of this crazy observation for arbitrary groups, although it's harder to state. And in that form, this is known as the Siegel conjecture, enjoys a long history in stable homotopy theory. And we still call it Siegel conjecture for some reason, but it was actually proven by Carlson. So let me write special form of the Siegel conjecture, proven by Carlson. Right. And one of the reasons why this is a pretty deep theorem is if you think about sort of the most obvious way to approach things such as the Tate construction would be to look at the Tate spectral sequence. But the Tate spectral sequence will give you something periodic, right? It will give you Tate cohomology on the homotopy groups of the sphere. So you have something periodic with values in the mysterious homotopy groups of the sphere, but then after the spectral sequence, suddenly you're left with something connective. So that means there's a huge mess of mysterious differentials there. So in other words, the Tate spectral sequence is not the way to compute this. The actual proofs rely on Adams spectral sequence technologies and very precise analysis of the Steenrod algebra. Right, so this is maybe to underline the deep role this Tate diagonal construction plays. And it's something very, very special to the world of spectra. The other thing that I want to mention at this point is that it also allows us to define a version of the Frobenius homomorphism on commutative rings. So for an E-infinity ring R, E-infinity ring spectrum, we have the so-called Tate-valued Frobenius which starts in R. This is now an E-infinity ring spectrum, not an ordinary ring. We take this Tate diagonal, which I'm just writing as delta, and then we go down back to R Tate CP using the multiplication under the Tate CP. So this uses that multiplication in an E-infinity ring is equivariant with respect to the trivial action on R and the permutation action on this tensor power. And one way to think about this is, what do I need to give an equivariant map like this? Well, an equivariant map like this is the same as a map from homotopy orbits to R. But this is something you can get out of the combinatorics of an E-infinity structure. For example, let me not say more about this because it might become confusing, but yes, this is something that's explicitly encoded in the structure of the E-infinity operad or something like that. Right, and so we do have this kind of Frobenius homomorphism, but it's actually not an endomorphism. It goes from R to some modification of R. And you can think of this as some kind of spectra analog of the Frobenius you get for ordinary rings, commutative rings. After modding out by P in the target. And maybe as a simple exercise, I want to suggest that you think about this and you check that this works for commutative rings once you mod out modulo P, and maybe also that this doesn't work if you don't mod out with P or if you're not commutative. Just to get a feeling for this kind of external Frobenius homomorphism. Right, so, but the cool thing here is that this guy knows typically much more about the ring you put in than just the mod P reduction does in ordinary algebra. For example, we saw over there that if you plug in something connective, then this is almost the same. It's the P completion, right? So then this is very close to being an actual endomorphism, even if, say, pi 0 of your ring was not actually characteristic P, right? So for example, you can do this on the sphere, and this takes you to the P-complete sphere. So this is kind of a very powerful refinement of what's going on in ordinary algebra. And in particular, if you apply this to to rings of the form map sigma infinity plus x E, where E is some ring spectrum, some commutative ring spectrum that you're thinking of as a cohomology theory here. So for example, this might be HFP for singular cohomology, or complex K theory, maybe P-completed complex K theory for P-completed complex K theory. Then these guys are commutative algebras using the diagonal on the space X. And if you apply this to this Frobenius homomorphism to that, you do get so-called power operations. Right. Sorry, I think I said something silly a minute ago, which is this, for our connective, this guy is of course not necessarily connective, this guy is. But for the sphere, they're the same. So at least for the sphere, this guy is just a P-complete sphere. Right. Right, and so these power operations that show up here, these include stuff such as Steenrod operations or Adams operations if you do K theory. So this is kind of a cool perspective on these things. Okay, so that's everything I wanted to say today. Thanks for watching, and we'll see you next time.